Hello, welcome to the research paper presentation as a part of our course CS643 Cloud Computing. My name is Neil Patel and today I'm going to talk about Lucas and on how to shuffle both fast and slow on a serverless architecture. It's a joint work with Himani Patel, Chinal Patel under supervision of our professor Borsha Christian. In this presentation, we will look at the various aspects of serverless architecture and on how Locus, an analytical model, helps in scalable analytics. Firstly, we will look at the motivation of the paper, followed by its central idea, design, implementation, evaluation, and conclusions. The content of the presentation is taken from the research paper Shuffling, Fast and Slow, Scalable Analytics on Serverless Infrastructure, published by Kefin, Sivaraman, and Ian Stoika. The past decade has seen widespread adaptation of cloud computing infrastructure, where user launches virtual machine on demand to deploy services on a provisioning cluster. Today, 83% of enterprise workload will be in cloud by 2020, of which 41% of enterprise workload will run on public cloud platforms. As the cloud computing continues to evolve towards more elasticity, there is a shift of using serverless computing, where storage and compute is separated by both resource provisioning and billing. In cloud computing, elasticity is defined as the degree to which a system is able to adapt to workload changes by provisioning and deprovisioning resources in an autonomic manner, such that at each point in time, the available resources match the current demand as closely as possible. In serverless architecture, pricing is based on the actual amount of resources consumed by an application rather than on pre-purchased unit of capacity. Now let's talk about the serverless trend. This trend was started by services like Google BigQuery and AWS Glue that provide cluster-free data warehouse analytics, followed by services like Amazon Athena that allows users to perform interactive queries against a remote object storage without provisioning a compute cluster. While the aforementioned services mostly focus on providing SQL-like analytics, to meet the growing demand, all major cloud providers now offer general serverless computing platforms such as AWS Lambda, Google Cloud Function, Azure Functions, and IBM OpenWhisk. In this platform, short-lived user-defined functions are scheduled and executed in the cloud. Compared to virtual machines, this model provides more fine-grained elasticity with sub-second startup times so that the workload requirement can be dynamically matched with the continuous scaling.
Now let's talk about elasticity in serverless computing. Fine-grained elasticity in serverless platform is naturally useful for on-demand applications like creating image, thumbnails, or processing streaming events. However, we observe such elasticity also plays an important role for data analytics workload. Consider, for example, an ad hoc data analysis job executed by TPC-DS query. This query consists of 8 stages and the amount of input data at each stage varies from 0.8 MB to 66 GB. With a cluster of virtual machine users, we'll need to size the cluster to handle the largest stage, leaving resources idle during other stages. Using a serverless platform can improve resource utilization as resources can be immediately released after use. Our key observation is that in addition to using elastic compute and object storage system, we can also provision fast memory based resources in the cloud such as in-memory Redis or memory cache clusters. While naively putting all data in fast storage is cost prohibitive, we can appropriately combine fast but expensive storage with slower but cheaper storage. Similarly to the memory and disk hierarchy on a local machine to achieve the best of both worlds. Approach the performance of pure in-memory execution at a significantly lower cost. However, achieving such a sweet spot is not trivial as it depends on a variety of configuration parameters, including storage type and size, degree of task parallelism, and the memory size of each serverless functions. This is further exacerbated by the various performance limits imposed in a serverless environment. Now let's talk about the main idea of the presentation, that is locus. Locus is a serverless analytics system that combines multiple storage types to achieve better performance and resource efficiency. In Locus, we build a performance model to aid users in selecting the appropriate storage mechanism, as well as the amount of fast storage and parallelism to use for MapReduce like jobs in serverless environments. Our model captures the performance and cost metrics of various cloud storage systems, and we show how we can combine different storage systems to construct hybrid shuffle methods. Using simple micro benchmarks, we model the performance variations of storage systems as other variables like serverless functions, memory, and parallelism change. Locus uses a serverless function as a service approach. The main benefit of serverless fast approach is the ease of deployment and flexible resource allocation. Now let us look at the MapReduce programming in nutshell. MapReduce is a programming model designed for processing large volumes of data in parallel by dividing the work into a set of independent tasks. It is a style of parallel programming that is supported by some capacity on demand style clouds such as Google's Bigtable, Hadoop, and Sector. Now let us see the stages of MapReduce in detail. Map is the very first phase in the execution of MapReduce program. In this phase, data in each split is passed to a mapping function to produce output values, which are sent to an intermediate shuffling stage. Shuffling consumes the output of mapping phase. Its task is to consolidate the relevant records from mapping phase output and send it to the next phase. In reduce phase, output values from the shuffling phase are aggregated. This phase combines values from shuffling phase and returns a single output value. Map and reduce function to be specified by program.
Let's take a look on system model and analytics on serverless. A driver process running on user's machine compiles the query into multi-stage directed acyclic graph and then submits each task to the cloud service provider. A task is executed as one function invocation by the serverless infrastructure. Tasks in consecutive stages exchange data via a variety of communication primitives such as shuffle and broadcast. Each task typically consists of three phases: read, compute, and write. Now let's discuss about different serverless model stages. Let's first look about input output stage. Input output. Similar to existing frameworks, each task running as a function on a serverless infrastructure reads the input from shared storage system such as S3. However, unlike existing frameworks, functions are not co-located with the storage. Hence, there is no data locality in this model. Fortunately, as prior work has shown, the bandwidth available between functions and the shared storage system is comparable to disk bandwidths. And thus, we typically do not see any significant performance degradation in this step. Compute. With serverless computing platforms, each function invocation is put on new container with virtualized computer core. Regardless of the hardware heterogeneity, recent works have shown that the almost linear scaling of serverless compute is ideal for supporting parallel workloads. Now let's talk about the important stage, shuffle stage. The most commonly used communication pattern to transfer data across stage is shuffle operation. The map stage partitions data according to the number of reducer, and each reducer reads the corresponding data partitions from all the mappers. Given m mappers and r reducer, we will have m multiplied by r intermediate data partitions. Unfortunately, the time and resource limitations imposed by serverless infrastructure make the implementation of the shuffle operation highly challenging. As we have seen before, to implement general serverless analytics, we need to implement shuffle. Shuffle is a part of key operations like join and group by. 70% of TPS DC queries uses shuffle operation. A direct approach to implementing shuffle would be to open connection between serverless workers and transfer data directly between them. However, there are two limitations that prevent this approach. Firstly, cloud providers do not provide any guarantee on when functions are executed, and hence the sender and receiver workers might not be executing at the same time. Secondly, even if the sender and receiver overlap, given the execution time limit, there might not be enough time to transfer all the necessary data. A natural approach to transferring data between ephemeral workers is to store intermediate data in a persistent storage system. The important question is how to implement cost efficiency shuffle in serverless architecture. We'll see in following slides. The main challenge in executing shuffles in serverless environment is handling the large number of intermediate files being generated. As discussed before, functions have stringent resource limitations, and this effectively limits the amount of data a function can process in one task. For example, to sort 100 TB will need to create a large number of map partitions as well as a large number of reduced partitions, such that the inputs to the task can be less than the memory footprints of a function. Assuming 1 GB partitions, we have 105 partitions on both the map side and the reduce side. For example, a hash-based shuffle on intermediate file is created for each mapper-reducer pair. In this case, we'll have total 10 billion intermediate files. Even with traditional cluster-based deployment, shuffling 10 billion files is quite challenging, as it requires careful optimization to achieve high network utilization. Unfortunately, none of the storage system offered by existing cloud providers meets the performance requirements, while also being cost effective. We next survey two widely available storage system classes and discuss their characteristics. To support the diverse set of cloud applications, cloud providers offers a number of storage systems, each with different characteristics in terms of latency, throughput, storage capacity, and elasticity. Just as within a single machine, where we have storage hierarchy of cache, memory, and disk, each with different performance and cost points, we observe that similar hierarchy can be applied to cloud storage system. We next categorized two major storage system classes. Let's discuss about slow storage. The majority of large-scale storage systems have been optimized for reading and writing large chunks of data, rather than for high throughput, fine-grained operations. Supporting large shuffles requires a more efficient and economic solution for storing intermediate data. One approach to overcome the performance limitations of slow storage system is to use much faster storage if available. Examples of faster storage are in memory storage system backed by Memcached and Redis. Such storage systems support much higher request rates, more than 100K requests per second, and efficiently handle objects as small as few tens of bytes.
Go.
Given the cost performance trade off between slow storage, for example S3, and fast storage, for example Elasticache, in following section we show that by combining these two types of storage system, we can achieve a cost performance sweet spot in a serverless deployment that is comparable and sometimes superior to cluster based deployments.
After knowing the main idea of the topic, now let us discuss about the design part. First, we will discuss the different approaches to shuffle. We first develop a high-level system model that can be used to compare different approaches to shuffle and abstract away the details specific to cloud providers. We denote the functions as a service, a module as compute cores or workers for task. Each function, invocation, or worker is denoted to run with a single core and W bytes of memory. The degree of the parallelism represents the number of function, invocation, or workers that execute in parallel, which we denote by P. The amount of data being shuffled is S bytes. Thus, the number of workers required in the map and reduce phase is at least S by W, leading to the detailed request of for a full shuffle S by W the whole square. The main storage characteristics that affect performance are unsurprisingly the read and write throughput in terms of requests per second and bandwidth in terms of bytes per second. However, we find that these values are not stable as we change the degree of parallelism and worker memory size. In figure, we measure how a function's bandwidth, denoted as B, to a large-scale store varies as we change the degree of parallelism, denoted as P, and the worker memory size, denoted as W. From the figure, we can see that as we increase the parallelism, both read and write bandwidths would vary by 2 to 3 times. Further, we can see that as we increase the worker memory size, the bandwidth available increases, but the increase is sublinear. Let's see an example with 60 workers, each having 0.5 G of memory. The write bandwidth is around 18 MB per second per worker or 1080 MB per second in aggregate. If we instead use 10 workers, each having 3 GB of memory, the write bandwidth is only around 40 MB per second per worker, leading to 400 MB per second in aggregate. The cloud storage cost is measured as follows. To measure the cost of each approach, we denote the cost of worker function as C dollar per second per byte. The cost of fast storage is counted as CFL dollar per second per byte. The cost of slow storage has two parts, one for storage as CS dollar per second per byte and one for access denoted as CA dollar per OP. We assume that both the inputs and the outputs of the shuffle are stored on the slow storage. In most cases, in practice, CS is negligible during execution of a job. In the figure, we can see the cost characteristics applied to all major cloud platforms like AWS, Google Cloud, and Azure. We propose a hybrid shuffle method that combines the inexpensive slow storage with the high throughput of fast storage to reach a better cost performance trade-off. We find that even with a small fast storage, example less than 1 by 28 of total shuffle data, our hybrid shuffle can outperform slow storage based shuffle by order of magnitude. To do that, we introduce a multi-round shuffle that uses fast storage for intermediate data within a round and uses slow storage to merge intermediate data across rounds. In each storage, we range partition the data into a number of buckets in fast storage and then combine the partition range using the slow storage. We reuse the same range partitioner across rounds. In this way, we can use a merge stage at the end to combine results across all rounds as illustrated in figure. For example, a 100 TB sort can be broken down to 100 rounds of 1 TB sort or 10 rounds of 10 TB sort. The cost model for the hybrid shuffle can be broken down into two parts, the cost per round and the cost for the merge. The size of each round is fixed at R. In each round, we perform two stages of computation, partition and combine. In the partition stage, we read input data from the slow storage and write to the fast storage, while in the combined stage, we read from the fast storage and write to the slow storage. To calculate time per round in the fast storage bandwidth is calculated as TFB equals to R upon BEFF. The slow storage bandwidth is calculated as TSB equal to R per B into P. The slow storage operation throughput is TSQ equal to R square upon W square into Q square. Thus, the time per round is TRND equal to 2 into max TFB TSR into TSB. The overall shuffle consists of S by R such rounds and a final merge phase where we read data from the slow storage, merge it and write it back to the slow storage. The time of the merge phase can be similarly broken down into throughput limit. TMQ equals to SW by R the whole square into TSQ. Bandwidth limit can be calculated as TMB equals to S by R into TSB. Thus, the total cost of the merge phase equals to T into max TMQ TMB. Therefore, the total shuffle time is S by R into total cost of the round plus total cost of the merge. The main source of stragglers for the shuffle tasks we consider in this paper are network stragglers that are caused by slow I/O to object storage. Network stragglers are inherent given the aggressive storage sharing implied by the serverless architecture. While some containers might get better bandwidth than running reserved instances, some containers get between 4 to 8 times lower bandwidth as shown in figure. To model the straggler mitigation scheme described above, we initialize our model with the network bandwidth CDFs as shown in figure. To determine running time of each stage, we then use an execution simulator and sample network bandwidth for each container from the CDFs. Further, our modeling is done for each worker memory size since bandwidth CDFs vary across worker sizes.
Now let us look at the implementation details of the locus model and how we can extend this model to improve it further. We implement locus by extending Firen, a Python-based data analytical engine developed for serverless environments. Firen allows users to implement custom functions that perform data shuffles with other cloud services. We augment Firen with support for the shuffle operation and implement the performance modeling framework described before to automatically configure the shuffle variables. For our implementation, we use AWS Lambda as our compute engine. We use S3 as a slow, elastic storage system, and for fast storage system, we provision Redis nodes on Amazon Elasticache. To execute SQL queries on Locus, we devise physical query platform Apache Spark and then use Pandas to implement structured data operation. One downside with Pandas is that we cannot do fine-grained pipelining between data operation inside a task, whereas in Apache Spark or Redshift, a task process records as they are read in or read out. We next discuss a number of extensions to augment the performance model described in the previous section. First, non-uniform data access. The shuffle scenario we considered in the previous section was the most general all-to-all shuffle scenario where each mapper contributes data to every reducer. However, a number of big data workloads have more skewed data access patterns. When a binary tree is used to do all reduce, each mapper only produces for one reducer and correspondingly each reducer only reads two partitions. Similarly, while executing a broadcast join, the smaller table will be accessed by every reducer while the larger table is a hash partition. Thus, in this scenario, storing the more frequently accessed partition on fast storage will improve performance. We only support this currently for cases like all reduce and broadcast join where the access pattern is known foreign. Storage benchmark update. Finally, one of the key factors that make our performance models accurate is the storage benchmarks that measures throughput, that is operation per second, and network bandwidth that is byte per second, of each storage system. We envision that we will execute this benchmark the first time a user installs Locus, and that the benchmark values are reused across a number of queries. However, since the benchmarks are capturing the behavior of cloud storage system, the performance characteristics could change over time. Such limit change will require Locus to rerun the profiling.
In this section, we evaluate Locus with number of analytics workloads and compare Locus with Apache Spark running on cluster of VMs and AWS Redshift. The section is organized as utilization and end-to-end performance with Locus on TPC-DC queries and then followed by CloudSort benchmark. Starting with comparing Locus with Apache Spark, we implement Locus on top of Pyren, which is Python analytics frameworks on top of service platforms, and AWS as a Lambda, S3 as a slow storage, and Redis as a fast storage. Locus serverless model can reduce cluster time by up to 59% and at the same time being close to Spark's query completion time by 2 times. Even with small amount of fast storage, Locus can greatly improve performance. For example, with just 5% memory, Locus can match Spark in running time on CloudShot benchmark and are within 30% of cost of winning entry. When running data-intensive queries on the same number of cores, Locus is within 1.61 slower compared to Spark. But compared to shuffling only through slow storage, Locus can be up to 4 multiplied by 500 times faster. Evaluate Locus on TPC-DC with scale factor of 1000, which has a total input size of 1 TB data on Spark SQL deployed on EC2 cluster and Redshift instances. Locus can save cluster time up to 59% while being close to Spark's query completion time to also beating it by 2 times. Locus loses to Spark only on query 1 by 20s. Locus provides better performance than running on cluster of 512 core VMs. Similarly, our cost performance model, we also find that if Locus Redis nodes have 25 Gbps links, the cost can be further reduced by 19% due to smaller number of nodes needed. Performance will not improve due to 25 Gbps links as network bottleneck, but because the latter requires on-demand provisioning of cluster, we can still prefer Locus over Redshift. Compared to Redshift, Locus is 1.56 times to 1.99 times slower. We run the CloudShot benchmark to compare Locus against both Spark and Redshift on reserved VMs. As we can see in this table, 13% of the cost for 100 TB record and achieve the same performance. Locus is even cheaper for 10 TB by 15%, but at the same time 73% more expensive for 1 TB. This is due to using fast storage based shuffle, which yields a more costly trade-off point. Locus is an order of magnitude faster than Spark and Redshift. The performance improvement is due to increase in parallelism that results in more aggregate network bandwidth. The cost reduction comes from both shorter runtime and lower cost for small memory sizes. For Locus reserved, performance improves with more instances while the cost remains relatively constant as the reduction in runtime compensates for the increased allocation. One key insight in formulating the shuffle performance in Locus is that adding more resources does not necessarily increase total cost. For example, increasing parallelism can result in better configuration. Another key insight is that using fast storage memory, sometimes even a small amount, can significantly shift resource balance and improve performance. However, such performance increase does require that we add resources in a balanced manner, as one could also end up incurring more cost while not improving performance. Now the question is, how much fast storage is needed? By using a parallelism of 40 with 2.5G worker memory size, Locus result in 3.21 times performance improvement and lower cost over using parallelism of 10 with 2.5G worker memory. At the same time, we can get worse scenario with 100G short increasing parallelism from 200 to 400 with 2.5G worker memory size makes performance 2.5 times worse. The big data benchmark contains a query shoot derived from production databases. We consider query 3, which is a join query template that reads in 123 GB of input and then performance joins of various sizes. We evaluate locus to see how it performs as join size changes. We configure locus to use 160 workers with Spark and Redshift, all totaling 160 cores. Figure shows that even without the benefit of elasticity, Locus performance is within 1.75 times to Apache Spark and 2.02 times to Redshift across all join sizes. Using a default storage only configuration can be up to 5 times slower.
Now let us get the main idea of the presentation through conclusion. With the shift to serverless computing, there has been a number of proposals to develop general computing framework on serverless infrastructure. However, due to resource limit and performance variation that are inherent to serverless model, it is challenging to efficiently execute complex workload that involve communication across functions. In this paper, we show that using a mixture of slow but cheap storage with fast but expensive storage is necessary to achieve a good cost performance trade-off. We present Locus, an analytics system that uses performance modeling for shuffle operation executed on serverless architecture. Our evaluation shows that the model used in Locus is accurate and that it can achieve comparable performance to running Apache Spark on provisional cluster and within 2x slower compared to Redshift. We believe the performance gap can be improved in the future, and meanwhile, Locus can be favored as it requires no provision of clusters. As we conclude this presentation, we would like to thank our Professor Borcha Christian for his constant feedback and support. We would also like to appreciate the work of the publisher. Thank you.